if there are no questions, then today's lecture will be about generative AI. I'll try to tell you something about how the modern systems work. It's the first time that I'm giving the lecture, so it's probably not as polished as some of the other ones. So if you have any questions, if something doesn't make sense even more, just stop me and ask, right? Also, maybe if you are interested in something a little different that I'm not really covering, then feel free to ask as well. Je všetko OK? Nemám to zapnuté? Jasně, v pohodě. Nič dôležité. Děkuji. Okay, so the plan for the lecture is pretty much this. I'll start talking about the differences between discriminative, which is the more traditional AI, and generative AI. I'll talk about self-supervised learning and why this is useful and different. And then I'll dive deeper into how large language models are trained. And then I'll talk about LLM agents, which are like more complex systems built around LLM, large language models. Okay, so discriminative versus generative. Like around 2010 plus, there was this big hype of deep learning, right? Things started to work. And at that point, gradually, we got into a state where anytime you have enough labeled data, you can train a classifier, an AI that will like transfer those labels to new data points, right? So the typical example is some object detection, right? So if you have enough pictures of balls and dogs and people, and you annotate them, you have like millions of annotated pictures, then you train some deep learning algorithm, and you will have a classifier that will be able to tell you whether there is this object on the picture or not, but potentially even where it is on the picture, right? Similarly, as we were talking about games, if you take some well-defined game, you have set of moves, and if you are asking which of the moves is the best one to do, again, you can base it on some human data, train it in a supervised way, and train. Then you can maybe even fine-tune it using reinforcement learning, but again, you have kind of a clear set of options, usually discrete, but it can be even like a regression, so the output can be a number, but it's relatively low dimensional output for whatever input you have, and you need examples. So similarly, it can be even more complex input. So it can be question answering, but not to have free-form answer, but just to take like one of the options. Again, option 1, 2, 3. You can process the text, and there were algorithms that were quite good at this. But still, the decision, the action eventually is to decide about something, to pick a move from a discrete set, to pick a class from some labeled data, right? So that was discriminative AI. Like generative AI was here even long before, but often didn't work super well. But generative AI is about generating new data. Like you don't have some labels, you just have the data, you have some data distribution, how a data point looks like, and you want to generate how the data point based on maybe some partial data point, based on maybe nothing at all. You just want to generate samples, you want to be able to sample from distributions, right? So the examples would be to have free-form answers to a question. Right? You will need to generate some text that will answer the question. And if you have enough data of answered questions, you can potentially do that. Like a well-known example that has been here for like a couple of decades is machine translation. Right? That's also a generative AI use case. You have a sentence in one language, you want to create a sentence in a different language. Right? It's not a simple decision. It's generating basically a new object of the same shape and type as the input data in this case. What is super like well-known and present in the media now are deepfakes, for example. So with these generative AI techniques, you can generate videos, movie, pictures, audio. So there are systems that can generate new symphonies. There are systems that can generate, like Sora, that can, we are talking about, to generate like full high fidelity videos of things that never happened, right? So this is generative AI as opposed to discriminative AI. And it doesn't sound like too big of a difference, but we will see in a couple of next slides that it's actually a huge difference in what we are able to do with these systems. So I was talking about supervised learning, where you have some input and label pairs. It can be an image object, it can be text and the sentiment of the text, whether it's happy, sad, angry, or whatever. You can have like a Rangan picture, and then you are asking whether there is a tumor. You can have a CV, and you are asking whether to hire this person, right? So all of these are supervised learning problems, and with enough data, you have it. For reinforcement learning, you need a little less data, right? You don't need all those labeled examples. So for example, in chess, you don't need for all the possible boards, like what do you play? You just need a simulator. And if you have the simulator, you can just generate strategies like playouts on your own. You will evaluate them using the simulator, and you can learn to play with just the reward function, right? Just the environment and the reward, what are you trying to maximize, right? So that's a little less information, a little less input that you need to put into the system, and you trade it for more compute usually. You need much more compute to train a reinforcement learning system. These generative AI systems are usually trained through something that is called self-supervised learning. So you just need data for it, just the inputs. You don't need anything else. You don't need labels. You don't need a reward function. You just need the inputs. And in general, you are trying to reconstruct the inputs. So you can do it different ways. Like the most straightforward thing are time series, where you will always take just part of the time series, and you will try to predict the next window, right? So if you have stock price, you will look at last 100 days of the stock, and you will want to predict the next day, right? And then you will shift it and look at another 100 and predict the next one. Shift it, look at the previous 100 and predict the next one, right? So you don't have any clear labels. You don't have any reward. You are just trying to be able to generate the data, to copy the data. A little less obvious, but also not too difficult, is mask data. So you can have a sentence, then you can mask out some words, some parts of that sentence, and then you can ask the AI model to reconstruct it, right? And again, you just need many, many sentences. You will take the sentence, you will mask out part of it, you will put it back to the model, and you will want it to reconstruct it, right? You can do the same thing in images as well, right? You will have an image, you will break it down to some patches, you will hide some of those patches, and you will ask the model to reconstruct it. Similar idea that diffusion models are using. You have an image, you gradually add noise, you just make it more and more noisy, and then you train a model to make the reverse step. So to have a noisy image and make it a little less noisy, and a little less noisy. And then if you start with a complete noise, and you will just iteratively apply this model, you will end up with a picture. You don't know what it is. With a different noise, you will end up with a different picture, right? But all of these techniques, there are many other self-supervised techniques, you can train without having any labels, just with have access to enough compute and enough data. Does it make sense? Okay. And now the big question, like if you are training these things using the supervised, like the self-supervised learning, what is it actually learning? Like what are all the things that the model needs to learn so that it performs these tasks? Input image and output image, yes. But if you think about the more semantics, like what is the knowledge that the system has to extract so that it is performing well on this task? Mm-hmm. Yes, but that's more mathematical view. Like, let's try to think about more semantics. Like, what does it need to learn, for example, in the text? Like, so that you do it well. What do you need to know about how texts look like, so that you are good at predicting some masked out parts of the text? Context is basically the input, but for example, grammar, right? Like, if you don't know grammar, it will be very hard to put the right word there, right? So you will have to learn grammar. If you look at a Wikipedia article and you want to predict that, and you mask out, I don't know, this word, right? You should learn that there are months, right? And that this is probably a month, right? There is some structure. If you mask out this word, English, in order to fill it in, you have to know that Alan Turing was English, right? So you need to learn some facts about the word. Like, just this seemingly very simple example of like filling in some masked up words. In mathematical terms, it's just minimizing some loss. It doesn't struck usually people how powerful it is. But if you remove like any parts of this sentence and you want to, with a very high probability, fix it, you need to understand the word, you need to know the facts, you need to understand the grammar, you need to understand the capitalization, the punctuation, like everything about the language in order to do it really well. Does it make sense? If we look at something a little different, like an image, and you imagine the masked objective. So what happens if I don't know, mask out this part of the image? What do you need to be able to fill it in? Yes, but what did you learn about the word? What do you need to know about the world, so that you can fill this in well? Not just perspective. You need to know, like, maybe it's not very visible on this picture, but that people tend to have dogs on the leashes, right? Right? It's like, if you just see this part of the picture, you don't see the dog. Then from the expression, from the leash, like, it's very likely that you should fill in a dog, right? If you want to minimize your error on, like, over all the pictures you have ever seen, that you will fill in this part well, then you need to understand that people tend to have dogs on leashes, right? Similarly, like, if you mask out like this part, again, what you are learning about the world is that dogs tend to eat from bowls because there is this tap. Okay, it will probably not be food, it will be water. Water is like dripping from the top, right? So there should be a bowl with water probably, right? That's the most likely thing. So just by this self-supervised objective, which starts with, just predict the next word, or predict some masked out words, or predict some part of the picture, you are learning a lot about relationships, about the facts in the world. And we can go even further. So if we have internet, so if we have a situation like this, it's a video. You can think about what will happen and what does the model need to know to predict what will happen. Okay, what does your model say that will happen? My model says that it will play a commercial from YouTube. Okay, I'm not online for some reason. Doesn't matter that much. I have the password messed up, so. Yeah. Of course. Right, so let's say that this is the input that the model is supposed to predict, right? Like, what is the next frame? What is some part of the frame which wasn't there? Right, so what does it need to learn? Yeah, it needs to understand physics, right? Like, it needs to understand that, okay, this bowling ball will probably be heavier, this like basketball ball will be lighter, and that they will be bouncing around and hitting each other. So in order to predict something like this super well, like to have almost zero loss, you have to understand a lot of physics. You have to really understand how the world works. Right? And this is the big promise of the generative AI. That's why everybody is investing so much into it, because people realize that if you just put a lot of compute and a lot of data to these models, and you will just let them predict things, then they'll have to learn a lot about the world, and then you can reuse it, right? So after you do this self-supervised pre-training, then the result is a foundation model. The model understands stuff, but it usually doesn't do much. Like, that's usually not the task you want to do, like to predict some missing part of the picture. But in order to do that, like, the layers of the neural network had to learn some deeper structures, some higher order features, some like understanding of the world, which can be reused for other tasks. So usually when you do this self-supervised learning, like you train it on many, many pictures, you will end up with a model, a neural network, which is called foundation model, which is very suitable for fine-tuning. So you will take this foundation model, you will usually like strip maybe one or two last layers of it, you will add a new bunch of clean layers, and you will continue training it for now much, much less data. So in the pre-training, you might want to use hundreds of millions of data points. And then for fine-tuning, it's enough to use a couple of thousands or hundreds thousands. And you can change the behavior of this model much quickly because it already understands the world. It understands how the images look like, what are the relationships between them. And fine-tuning them for a particular task, like face recognition or anything like that, now requires way less data than before. So in the recent years, this is probably the most common paradigm for building AI systems, that you will pre-train it on a huge amount of data just to understand the domain, and then you will fine-tune it on some particular problem. Questions? Okay, so that's self-supervised learning, and that's what's behind the language modeling, the whole paradigm to a large extent. So language models are, the foundation language models are basically the self-supervised learned models of language. What does it mean to model a language? So first of all, you need to know what is a token. Token is some minimal, unbreakable, further unbreakable fragment of text. In the current systems, it's usually something like 1/3 of a word, or 3/4 of a word, like something a little bit smaller than a word. That means that very common words are one token. Some rare words can be composed of 2 or 3 tokens, but there are models which are actually on the character level. It's just less efficient. There are models that could work with the whole words, but usually just to keep things optimally efficient, there is some notion of token, which is a couple of characters that often appear together in words. So that's a token. And then in the language modeling task, you want to learn distribution of sequences of tokens, right? So a text is just a sequence of tokens, and the goal is to create a model that will be able to sample this probability distribution of sequences of words, right, of any texts. And we know from Bayesian networks that an efficient way to do that is to actually decompose this huge probability distribution on all texts to using a chain rule to just conditional distribution of the next word depending on all the previous words, right? And that's what LLMs actually are, right? They are just neural networks which we were approximating as function approximators, right? For some input, it will give you some output. So the input is a sequence of words, previous words, and the output or tokens, and the output is the following token, right? This is the problem that LLMs, even like the newest one, like GPT-4, whatever, are solving. This is the key problem in the middle. Is it clear, or are there any questions? So an example, if you have a sentence like the cat sat on the, then this would be the input. It would be split to 1, 2, 3, 4, 5 tokens probably on the input. And the question is, what is the probability distribution over the following token? And in this case, it could be a mat, it could be a table, it could be a banana, it could be a D, right? Like usually the number of tokens in the system is like tens of thousands. So you would actually predict every single token, like what is its probability in the model. And you would expect that if the model is well trained, then mat or table will have much higher probability than a banana or D, right? Because D would be agrammatical. Like you cannot have DD. So that just doesn't make sense. It has very, very low probability, but mat has probably a rather high probability, right? So this is the language modeling problem. And that's it. Basically, that was the big breakthrough, that people did this, and they realized that when they are training larger and larger models, it just works better and better, and that it can do things. So how did they train it? This is results from GPT-3, which is probably the last of the major models which was like well described in literature, that OpenAI was still publishing all the details about how they train it, what they train it on, and everything. Like afterwards, people realized how big commercial value it has, and the largest labs stopped publishing these details. So this is the composition of the text. So the problem was really just predicting the next token. So any text you can get, you will always split it to some prefix and the next token. These are your training data. You will use self-supervised learning to train it, right? Is that clear? And now what data are you using? So the vast majority of the data is this common crawl data set, which has been available even before to researchers, and that's just like somebody crawled the internet and tried to clean it a little bit. But it's 400 billion tokens, right? Billions are 10 to the power of 9. So it's some 4 to the power of 11 tokens of just data from the internet, any web page that the crawler could find, right? So that's 60% of the data that GPT-3 was trained on. Then it was used on trained on web text. Web text is a very similar project to the common crawl, so there potentially are some overlaps. They were trying to remove them, but again, just raw data from the internet, raw texts from the internet, another 22%, right? So over 80% of the data it was trained on are just random texts from the internet. So no guarantee of being correct, no guarantee of being somehow specialized, making any sense. But if you are trying to learn like grammar and you are trying to learn how people tend to communicate and everything, then this is super valuable. Then 8% were some books databases, or 2 times 8%, where hopefully they claim some open domain books, but we know that afterwards people made analysis on what it was trained on. How would you make an analysis whether this kind of a model was trained on your book or not? Just a check that you understand what it's doing. Right, you wrote a book, and now you are curious whether OpenAI has trained. Yep, so you take a chapter, you take a paragraph, you put it there, and you see whether like it will continue with the next paragraph or whether it will complete the paragraph of that book. Like if it's over some threshold, it's like plagiarism, right? Like nobody could write the book exactly the same way as you wrote it unless they saw it and actually remember it. So if the similarity of what will be continued is too much, close to the original text, then you can conclude that it was probably trained on that. So they used like together 16% of the data were books, and then 3% of the data was Wikipedia articles in particular. So again, they tried to remove them from the common crawl and web text because they were somehow included, and crawled Wikipedia again because that's the most like high quality factographic data that you can find freely on the internet. Right, so altogether, it was still in the order of hundreds of billions of tokens. And then usually they train a range of models, right? They just don't train from scratch the huge model, which costs tens of millions of dollars at least to train. They train a sequence of smaller models as well. So for GPT-3, this is not even complete list, like they've trained many more of them, but train models from like hundreds of millions of parameters up to the largest one, like the GPT-3 that was behind ChatGPT was 174,000 million, so 174 billion parameters, right? So it's a neural network, and it had this many parameters, and in order to train it, they needed like 3,000 petaflop days. Like we were, petaflop is 10 to the power of 15, I guess. Right, flop is floating point operation. So it is a huge amount of compute. Like if you remember, I was showing some of those largest clusters, largest data centers before, and they were on the order of, I think, 1,000 less of this. So these trainings actually take a couple of weeks, maybe 2 months, this pre-training stage. And they were able to like usually make not even one epoch, right? So here they say that they train on 300 billion tokens. So they went through maybe half of the data they had in GPT-3 training. Like since then, the newest model like GPT-4 and so on, they are training on even more data and more compute. But it's like maybe one order more of data and compute. It's hard to get even more than that. And then there was some model architecture. I'll not go into details of that. Like if you take any course on deep learning and neural networks, you will learn more about that. But basically, it is a feed-forward network architecture. So you have some inputs, and then you have many layers, like 100 layers of this kind of sub-architecture, which again are some mathematical functions that you are doing with the data. So on the input, you have some data, and then you multiply it with many weights. You sum it, multiply it, and at the end, there is an output. And what it does in the text is that you have the tokens, like the representation of the tokens, individual, like you can think of words on the input. And then you have on the output the same words but shifted by one, right? So these words will be the same as these words, but then there is one more here, right? And that's the next word you are trying to predict. After you predict it, you put it back down, and you predict again, and you predict the next one. And again, you will put it down. And this is called like autoregressive decoding, that it is always taking its own output, putting it back to the input, right? It means that it will output the next word, the next token. It will put it as the input of the network. It will predict the next token. It will put it into the input, and so on and so on. Right? And I would just remind a bitter lesson here, because this is pretty much all you need to train GPT-3, right? You need this neural network, which is not that complicated. You need a huge amount of data and a huge amount of compute, and you create something that is able to do machine translation, question answering, all sorts of text-based problems much better than anything before. Like before, people for decades were trying to like use linguistic knowledge, like trees of decomposition of the words that you have trained on in a grammar school, right? Like what is the subject, what is the object, like encode all this knowledge about how we are thinking about language into computers to like do things like machine translation and summarization and whatever. But then just this kind of simple neural network, huge amount of data and huge amount of compute, produce better results than all of those decades of trying to encode human knowledge, right? Any questions? Okay, so what does it do? What does GPT-3 model do? This is one example from the paper. So if you start with something that looks like an article, you will write a title, you will write a subtitle, then you will write this word article. So this great thing is something that you would write into the model. And then you just let it generate. Like again, it generates next word, you put it into the context, it generates next word, you put it into the context, and so on and so on. And you do it until it generates some end of text token. So usually you would put in the training some special token that says like this is the end of the text. So when it generates, you will say, okay, this is the end of text, this is my output. This is rather general. So if you put really long list of like question, answer, again, the natural thing after the next question will be answer to that question. But if you want it to do something different, something more, like you want to ask it to give you a description of, you want to use it for brainstorming, for example, right? You want to ask like, what options do I have for my next job, right? And that's something that doesn't appear on the internet that often, right? So it will do something, it will output some texts, but usually it will not be super nice. So in like half of the cases, it would give you something useful. In half of the cases, it would give you something that looks like a text on the internet, which is not entirely what you wanted, right? So this is just the foundational model, like the pre-trained model that knows a lot about the world, that can generate the text, but that's not exactly what you want. So what do you want to do with it? Like in the paradigm of self-supervised learning, you want to fine-tune it to perform well on some tasks you care about, right? So the first thing that people do with these language models is instruction tuning. So they want to fine-tune the model to follow instructions, right? So that it doesn't just generate articles, it actually has a conversation. If you give it a task, it will try to complete it, right? Are there any questions? Like you seem to be very like unengaged? Like, is it something clear that everybody knows and understands that I'm talking about, or is there some other reason, like question how, like what you would be more interested in? So who understood most of what I was talking about so far, like before I was talking about it? Okay, so you had some idea, but you didn't really know clearly. So okay, I'll just try to continue. So the instruction fine-tuning is trying to kind of tune this language model to be better in following instruction. And how do you do that? Like, you can use the supervised learning paradigm. And for that, you would need now much smaller. So after the hundreds of billions of tokens of pre-training, you just need some tens of thousands, hundreds of thousands examples of instructions and output pairs, right? So you will actually want to have examples of this is what the user wanted, and this is a good answer for that question. And then you want to fine-tune. Fine-tune means that you will just continue training the language model. So you'll continue predicting the next word just on this selected data set, which is just for instruction following. And they did that. So OpenAI employed huge amount of, not that huge amount of people, but they spent a lot of time on it. Some like larger tens of people who were actually writing this by hand, right? So they were looking at what can be an interesting question that people would have. And they had some early like users before it became super public. So they took what people are asking, and they had other people actually write an example answer, like how would they answer it well. So this was an expensive process, but it created some sort of data set, and then they fine-tune on that data set. And it included things like question answering, text summarization, translation, code generation, creative writing, and reasoning, right? So they created this data set, but it was lengthy process. There are still some things which like they didn't cover, and it was super expensive. So they were trying to think of some better way how to do it. And they came up with this reinforcement learning with human feedback paradigm. So how did that work? So they figured that having people like write those articles is the most like expensive part, but it's much easier to just evaluate like which generated article is better than another one, right? So instead of having people write it from scratch, they used the model to generate a couple of options, right? So they would generate k options, and then they would ask people just to order them, like which of the options is better than another. So you can imagine like this. So you have prompt explain the concept of entropy in thermodynamics. And then you can have k, let's say 3 different responses, and you will just sample them from the model, right? So you can just have 3 different random samples. You can maybe add some additional instruction like try to be formal, try to be clear, or something like that to make the answers a little bit more diverse. And then you will ask people to order them. And they would say that, okay, this is probably too much, too many formulas, I don't like that. And out of these, they are pretty similar, but yeah, let's say I prefer this one, this would be second, this would be third, right? So you would have them order which they prefer the most. And then you will use this data to do this reinforcement learning with human feedback. So you will collect the comparison, you will sample pairs from that, pairs of 2 things which like the person prefers one to the other, and then you will train a reward model. So you'll train another neural network, which can again be some pre-trained language model, but usually much smaller one, to do this ranking the same way as the people do, right? So you will try to, like in this case, not rank, just try to create some kind of a preference function that would say like how many points out of 100 would this text get, right? And if you have two texts, you know that the human prefers one to the other. You know that the one needs to have more points than the other, right? And that's how it's trained. So you will just train on these pairs, and you will always train the neural network so that the preferred one has more points than the less preferred one. You train it on many, many pairs, and then you have this reward model that is now independent on the original data, right? It's you can give it any new text, and it will tell you how much the human would like it, right? So not only the like thousands, tens of thousands of texts that people saw, but you can generate brand new texts and ask the reward model how good it is. And if you have this, you can use reinforcement learning, right? So you can create an environment. In the environment, the LLM will just generate the new text. It will put the text into the reward model, and that will give it some payoff, right? And it's the same kind of reinforcement learning as you have seen in our classes. So after generating enough of the outputs and getting a reward, it's just gradually improving and generating more often the texts which have higher reward. And they use some proximal policy optimization algorithm. That's not that important. Like they could have used like any sort of reinforcement learning algorithm with this reward model to improve it even further. And this seemed to work very well and generalize from the relatively small amount of human labeled data. Questions? No questions? Okay, so this is the whole process that they used to create ChatGPT, right? Like the first ChatGPT that was released, this is basically how they do it. And now they didn't know how to use it on their own, right? Like after this process, like you don't know what is the best prompts, like how do you work with it? There is not much like guidance, so people had to figure it out. And there was this huge boom where people were playing with it and finding out that it's actually powerful in doing things. And a new kind of field or job of prompt engineer and prompt engineering appeared. So people specialized on how to write the prompts, the instructions for the LLMs in an efficient way so that it does what they want. Because if you have experience with that, you know that sometimes it does what you want, sometimes it doesn't. And there are ways how to write it better and ways how to write it worse. And the prompt is now the term that is called for the beginning of the generated text so that the LLM can continue and generate the rest. So this would be the example. The prompt can be like, what is the capital of France? And you would expect it to say the capital of France is Paris. And people were playing with it a lot, and you will find like huge amount of blogs and even like from reputable companies, instructions like how to write these prompts well. And it worked somewhat at the very beginning, but then as the models got better and better, these kind of small optimizations like you should use bullet points to explain the things. You should always formulate it as positive and not negative. And there were instructions like recommendations like this, which worked for the earlier model, but as the models got stronger, it kind of stopped working and wasn't that important. But there are still some kind of key recommendations or techniques which are super useful and used up to today. And one of them is this few-shot prompting or few-shot learning. Who knows what it is? What is few-shot learning or few-shot prompting? Good. So like when you want the LLM to do something, it's handy to, with your instruction, include a couple of examples. Like the LLMs are very strong at repeating patterns. Like if you give it some especially syntactic patterns, like the architecture as it is built has strong bias to repeat that pattern again and again. So if you want to do something like translation, you can just ask it translate English to French. That would be called a zero-shot prompt because it doesn't give it any example. If you include like a couple of examples, those are called the few shots. So you would just show that English in English sentence is like this, French in French the sentence is like this. English, French, English, French, and you would keep it like that. So this is really the prompt you would write into the LLM. And if you have it complete the sentence here, the performance tends to be much better, like tens of % better than without these examples. And you can train it to do like very new things. So you can actually train classifiers. That's why it's called few-shot learning sometimes, that you can modify the prompts, put there like 50 examples of things that you want, and you will have a classifier, right, of any kind of property. You want to do sentiment analysis? Okay, you will take 50 different posts, like for Twitter posts, for example, or comments in some reviews. You will take 50 different comments. You will say this is a positive sentiment, this is a negative sentiment. It will give you sentiment analysis. But this is kind of clear because you would expect the model to know what is a sentiment. But you can learn your own new property, right? You have your company, and you want to know whether like this is related to my company or unrelated to the company. Like ChatGPT may not know what does it mean, but if you give it like 50 texts, you will say about 50 texts that these are related and these are unrelated. You will immediately, without actually training the weights of the model, you will create a new classifier which will give you documents which are related and documents which are not related, just by giving a couple of examples, right? So this was a big, again, unexpected breakthrough that these classifiers actually work very well. And now in practice, when you are trying to do a new classifier, very often you would just start with this without training anything. You will just give it a couple of examples and see how well it works. Often it works well enough, you don't have to do anything else. Right? So this is called few-shot prompting or few-shot learning, that you give it clear examples. Questions? Okay. Another technique is called chain of thought. Who knows about chain of thought? Some? Good. So when you are generating text, even people, when you are thinking about some problems, if I ask you like, this is a problem, give me an answer, you will be guessing most of the time. Like if you want to give proper answer, you want to think about it. And what you are doing when you are thinking about it, you are breaking it down to some steps, and you are thinking about like, okay, if you have an example like this, like the cafeteria had 23 apples, if they used 20 for lunch and bought 6 more, like how many apples do I have? If I just ask you now, give me the answer, you will not know, right? You will have to think about it a little bit and say, okay, so it was 23 before, after they removed 20, so they had 3, then they got 6 more, so now they have 9, right? And without doing this kind of thinking, it's very hard for you to give the answer. And the LLMs behave in a very similar way. So if you let them not give you the answer, but do this thinking, like just output the sequence of tokens which are doing this kind of chain of thought, then they perform much, much better. And people just realize that you can do simple things like this. Any prompt you put, if you just add, let's think step by step at the end of the prompt, the models tended to do this, tended to start breaking down the problem to steps and eventually give you much better results. And as with other techniques in these LLMs, like once people realize that this kind of works, they started fine-tuning the models to do it well, right? So they understand that this is a pattern, how the LLMs tend to provide better results. So they generated a lot of data of these chains of thought, and they fine-tuned the models so that they are better at generating these useful chains of thoughts. right? So again, it's a rather simple technique. You just put it there, and now there was in the last years a lot of these reasoning models. So the reasoning models are actually nothing different than these chain of thought models, which are fine-tuned to do chain of thought, and some of them can hide the chain of thought in some like special tags. So again, you can have some post-processing of the output, which we'll be using even later, of the LLM. So LLM can generate these kind of chains of thought, but you can train it to generate first the token, now I am thinking, let me think, and then a token, I've finished thinking, and now I want to write the output. And then just in the user interface, you can hide this thinking, right? So you can have it, when it outputs this I'm thinking, you will stop outputting it to the user. You will let it write whatever it wants to write. Then when it outputs I've stopped thinking, you will continue outputting it to the user, right? And this is basically what the thinking models are doing. They are doing a hidden chain of thought and then outputting the results. And that's why DeepSeek was super popular in that they showed it for the first time and people were not really aware of it, and they like to watch it, and that's how DeepSeek gained popularity. And then even the other like OpenAI and Gemini and so on started showing the chain of thought. But before that, it was the same thing, just hidden from the view of the users. Why did they hide it? I think it's an interesting thing to understand. No, like it is happening anyway, behind the scenes, before it gives you the answer. So the tokens are the same. Again, because of the competition, right? Like the most difficult thing about this is to give good examples. So that's why DeepSeek was like so successful, because once somebody already publishes, you have already some data available, you have some of these chains of thought already available, then it's rather simple just to fine-tune on them. But creating the right chain of thoughts to train on is actually expensive. So that competition cannot just take those chains and fine-tune their base models, because everybody, like the previous slide, this is trivial, like this is 500 lines of code and insane amount of compute, right? The next hard step is to have really great examples that will fine-tune the model to be really useful and to do the good reasoning traces. So that's why they were trying to hide it, and the Chinese didn't care. They showed it, and then everybody shows it because it doesn't matter anymore. Okay, so that's a chain of thought. Is it clear? Okay, and the last technique that I wanted to talk about is this retrieval augmented generation, also super popular. And again, it's using this kind of idea, which we will see once more, that you can be looking at what the LLM is outputting so far and use it to perform some actions. And LLMs are good from how it's trained in having some kind of broad context, right? Like they've seen everything on the internet, they have some idea about everything, but then if you want very precise knowledge, very precise data, which are current, for example, right? Like you want to know what happened yesterday, you want to know what is the weather somewhere, or like we'll talk about that later, but you want to know some knowledge, like the database of your employees, you want to know who's boss, right? Some very specific knowledge, which wasn't on the internet, and even if it wasn't there often enough so that the model can use it, right? So that's why you often want to include some specific data in the model. And again, like, is it a drill or? Let me check. ignorujeme, hej? Evakuácia, jo? Čiže aj študentov preč. Okay, evacuation. I'm not sure whether it's a drill or not, but we are supposed to leave. Okay, so let's continue. Like, I expect some people will still come, but let's try to use the time. So I was talking about retrieval augmented generation. So when you are generating something from the LLM, you can be kind of looking at the trace so far, like what you have generated so far, and guess what is the useful knowledge that the LLM would know. You can already look at the input, at the prompt, and based on the prompt, like if the prompt is about your organization structure, like who is boss of who, right? You can detect, classify that this is something that will need like specialized knowledge, and you can try to use again LLM to transform the prompt into a query, to a database. Then you will fetch the data from the database, and you can add it to your prompt, right? And this is called retrieval augmented generation. So there are different methods how to do it. A side product of these LLMs are like vector representations of semantics. So very often what people use for these RAGs is to look at some internal states of the neural network, which are just numbers. And then you can do a similarity search in these vectors of numbers to find states which are semantically similar, and based on that, fetch some documents from the database. Yes? Okay, I can try to turn it on and off. No, none of them works. Great. Okay. So the process is simple. There is a user query that goes into a retrieval system, which looks at whether the query requires some specialized knowledge, or it can always just take the semantic representation, whatever that means. I don't have time to go into details of what that means, of that query, and then can make a similarity search in a bunch of documents and find like the most similar documents to the query, like which are talking about the same thing, and you would just put them into the context. Right, so you would just add them under your prompt. So the user want to know who's boss, and you will then add, like, this is the organization chart. You will put there all the data, and they say, and now generate the answer. And you will just like send it back to the LLM, and now LLM will have all of this new knowledge in the context, in the same way as if it has just generated it, right? So it will be able to refer back to it, and will generate the answer and give you the response, right? How you do this retrieval can be really varied. Like the simplest system can be just keywords, right? If there is some special keyword in your query, then you will just add this additional knowledge. If you want to do something more complex than these kind of vector databases with semantic representation of that word, of that query can be used. And as I said, you can even run it later. Like you can look at what you are generating, and even though from the query it's not clear that you would want to include some knowledge, when you start generating and you come to some things which you are talking about, you are not sure, or the model like is just putting it out of their head, so you are not sure that will be correct. You can even stop the generation, add the additional context from the database, and then continue the generation, and it will refer back, right? Because these LLMs are autoregressive, so they are always looking at everything before that they have generated in order to generate the next token. This has some limits because the context is not infinite, and especially in the beginning of the LLMs, it was just like 500 tokens or 1,000 tokens or something like that. So there you had to be very careful, like if you were doing this retrieval augmentation, to put there only the very necessary things. But currently, the new models have like millions of tokens of context, so you can be much more wasteful with that. But usually you pay for it, right? So still, you want to be somehow moderating it, right? So retrieval augmented generation is just a way how to include some hard facts, some hard knowledge in the generation of the LLM based on some databases or external sources. Very often, like if you want to make a specialized chatbot for some domain, right? You want to have a chatbot you want to talk to about ZUI. You would take all the slides, you would put them into the rack, and then when you are chatting with it and you start talking about some topic, it will find the right slide and it will include the slide in the context so that it can give you the exact things that were relevant for you based on this data that you gave it, right? And there are tools like Notebook LM that we mentioned before, which are like pretty much based on this. The OpenAI GPTs are also based on this, right? Like you create a new GPT, which is just a new system prompt, so something that will be in front of all of your prompts. There will be another prompt which is defining the behavior, and usually you give it a set of documents that it should work with, and it will work with it through this RAG system. So when something comes up in its reasoning or in the prompt which is related, it will fetch the document and put it into the context. Questions? Okay. So these are the basic techniques, like how to build the language model and how to use it. And then, of course, people are heavily interested in comparing the LLMs because there are huge investments. If you want to raise a new round of money for your AI company, you need to show on some benchmarks that you are better than the others. And one of the most popular benchmarks is this chatbot arena, and it's nice in that it's I need to show me the leaderboards. I wanted to show this kind of window as opposed to other benchmarks which have some given set of problems that they are testing on. Like this chatbot arena is just crowdsourced. So it allows people to come there to give their prompt and get answers from different LLMs in a blind way. So they don't know which LLM gave them the answer, and they are just voting like which of those answers they prefer, right? And based on that, they are creating a ranking of the models, like which is the best model for humans, for their direct interaction. And so they have the result in a form of, okay, it's the other way around, of this leaderboard and the score, where they are showing that currently the best models are Gemini 2.5 Pro, then OpenAI O3, O1 latest, and so on, right? So every time somebody creates a new bot, they will submit it here, and people will play with it. It will get the comparison with the others, and if it is preferred more often than the others, then they are going up in the ranking, right? And this is again something like ELO ranking, which is trying to pick the strongest one. Yes. Yeah, this is like it has been used in the past several times that companies launched secretly their chatbot into this before they actually openly released it, right? If they just want to test how good it is, they would put it here under some fake name. And it happened several times in the past that completely unknown fake name just raised to the very top. And then people were speculating, and it was also a good PR stunt. Like, who is that? Who is that? And in a couple of weeks, they announced that, okay, it was us. So it is used this way, but there are now the evaluation is whole business. Like, there are companies which will do the evaluation for you. All the big labs are doing a lot of evaluation. Like, they are investing a lot to evaluate not only the quality, but also the safety and other things. What is the problem with this kind of evaluation? I don't know whether you have heard about the Llama 4 scandal. You can call it cheating, but again, as always, the preferences of people are something different than like usefulness for other things. So it is not that hard to fine-tune the model for this specific use case so that people like it, right? And people like flattery, people like when it agrees with them, and when it puts a lot of emoticons and whatever. So now you have to be a little careful because companies started to optimize for this, and every time you create some kind of a benchmark and people start optimizing for it, there is like a law that is saying that the benchmark stops being useful anymore because people are just trying to be nice and like target emotions and not being useful anymore. But we still have other benchmarks. So this is another like quite popular one, which is based on set of problems from all sorts of domains, like math problems, question answering problems, summarization problems, and so on. Like, as people are developing these LLMs, they are building up new and new data sets of problems. And if some data set becomes really popular, they would include it in these leaderboards, and they compute some like average performance. And it's actually a very important part of that space to have independent evaluation, right? So that everybody can lie about their own models, how great they are, but then you have these kind of independent entities, which every time a new model comes, they will include it. And why I'm talking about it is because if you want to use a model for your project, then I would advise you to open a leaderboard like this and try to look at like which of them are good at the type of problems you care about, right? So here you can read about what exactly the benchmark problem is, but then you can find the model which works really well for you and has the right cost, and you can potentially get it even offline. Like many of them, like these quants, are often open source models that you can just download and run on your own hardware. Okay, so that's benchmarking. Next important thing I wanted to quickly talk about are LLM agents. So LLM is a reactive system, right? You, like a chatbot, typically you ask it a question, it gives you an answer. Maybe you ask it a question, it fetches some additional data from the database, it gives you a question. But that's it. And that's not very useful and not very dangerous. Like, okay, it is kind of useful, but not as useful as it could be in this form of an agent. So we already mentioned the agents in reinforcement learning. So agent is just something that is able to have this kind of loop of perceiving the environment, reasoning, planning what to do, taking some actions, reflecting on the result of the actions, perceiving the environment, taking reasoning, taking actions, and so on and so on, right? So this is called an agent from like very old times in philosophy and so on. And now, what can you do? And people started to do it immediately when LLMs came out, is to use LLM as kind of a CPU of an agent. If you just create a for loop or while loop, while true, and you will always just perceive some environment, put what you have perceived into an LLM, ask it, what do I do now? Take the action, execute it in the environment, get the new observations, put it into the LLM, ask, what do I do now? You have created an agent, right? And you have created a rather powerful agent, which understands a lot about the world, which can do a lot of things, but can only talk. If you add some small additions, then it can do more than just talk. So LLM agent has this LLM as a core controller, like most of the tasks are done through that. It has memory, so if you have this repeated interactions, you want to remember some of it, you don't want to remember all of it, you want to maybe structure the memory in some more structured way, in some database, and then you want to be able to query the memory to like fetch only the things which are relevant for your next decision. It has some sort of a planning module. And again, it can be planning in a way that we were talking about here as planning, but very often it's super simple planning, again, just by prompting. So you will ask the LLM, I have this complex task, right? I want to, do I have an example there? Don't have much time, so I'll get to the example later, but you can have a complex task and ask the LLM to give you steps which you have to perform before you can complete the task, or how do you complete it? And then you can take each of these steps and try to execute it. And the most important thing that I wanted to talk about in more depth is tool use. So these LLM agents can have additional components which are not LLM based, which they can call, such as search, such as calculators, such as Python interpreters, and so on. So this is how it would work. So you have prompt, find a current weather in Prague and send an email summarizing it to John, right? You can ask this to an LLM agent. And the agent will use planning, so it will just ask, if I want to do this, what are the steps that I need to do? And it will output, okay, so I should get the weather through some API, I should format the weather information, and then I should send email through some API, right? And then you can just execute it. There are frameworks which will allow you to do that. And the important part, like I'm running out of time, so I wanted to get to this slide. The important part is the tool use. So the tool use allows the LLM to call any function. Many of the APIs, so you can chat with the chatbot through like a window, but very often you will just call an API calls to the backend systems. And in the API call, you can give it a list of tools. And tool is just a function. You will give it like the name of the function. Usually it's executed as a cloud function somewhere like on the infrastructure. You will describe what the function does in plain language. You will describe the arguments and what the arguments are in plain language. And then you will, in the API call to the LLM, you will say that it has this tool available. And what it does is, again, it gets the information about it into the context. So you will give it the prompt, and then you will add something like, and you have these functions you can call. These are the descriptions of what they do, and these are the parameters they need. And then when the LLM wants to call the tool, it will just output a special token, which is saying, now I want to call a tool. And then it will just say that, okay, it wants to call a tool, get current weather. It knows that because you described what it does, right? So based on this description, it understands that this is the tool it wants to call. It understands that the parameters it needs to provide is this. So the LLM will just generate this text. And again, the framework around it will be following what the LLM is outputting. When it sees that it outputs this kind of special token, I want to call a tool, it will take this definition of what is calling, execute the function, get the result, put it into the context again as, okay, this was the result of the tool call, special token, the results, and let it generate further with all of this in the context, and then it can generate the current weather in Prague is sunny and temperature and humidity, right? And this tool can be not just weather, it can be calculators, it can be Python interpreters, right? So you can even say, okay, I want to run a Python function. This is the body of the function. Just run it and give me the results. Like the LLM will say it for itself, the system will do it for it, and then it will continue with the result. It can be search engine, right? So very often LLMs, when they are not sure, you can tell them, okay, if you are not sure, you can just call Google and you will get like top 10 results of Google, and it gets it into the context. So the next tokens it generates, it can refer to the previous results from the Google search, right? And it can use the knowledge, the information it found in the search. So this is the thing which is actually has a huge potential and huge danger as well. Because once you just let the LLM work like this, like you spin up a cloud instance, you will run there an LLM, you will give it access to the internet, and you will let it do whatever, right? Then it can become dangerous, right? It can send emails, it can make calls through the tools, it can search for additional data, and it can get out of control. Doesn't mean that it will become conscious and want to kill you, but it can actually do a lot of damage before somebody understands and realizes that there is this rogue thing which is doing things on their own, and nobody knows what it is. Like, I can very easily imagine that many people will try, like, here you have $1,000, turn it into $1 billion, like, go, use as much compute as you can, just do it. I don't care how. And if you run agents like this and let them like do whatever they want on the internet, that can become dangerous. And that's why the next lecture will be about dangers of these agents. Limitations are still large, so the systems are not very reliable. They don't understand what they are doing. Still, like these agents, I was just saying, okay, you will put this into the context, you will put that into the context, you will just let it do the chain of thought, but all of these are tokens. And tokens are now very cheap, but all of this can be like tens of thousands, hundreds of thousands of tokens for every call, for every loop of that agent. And it adds up, and it's still very costly to use for many use cases. And we'll be talking more about the safety concerns the next time. And this is just the summary. So generative AI learns to generate new data as opposed to the like making decisions about the data, right? Generative AI models are trained by self-supervised learning paradigm. That means that it doesn't need any labels, but it is trying to like reconstruct, predict some parts of the data, which is super strong to create these foundation models which are not doing much, but can be easily and cheaply fine-tuned to do specific tasks. LLMs are just like application of this idea on text, and you can have advanced prompting techniques like chain of thought, like few-shot learning, like RAG, and then you can loop them into LLM agents, and then it becomes interesting and it's doing a lot of stuff. Questions? Okay. If no questions, then thank you. Next time is the safety lecture, and that will be the last lecture. And then there are the exams, which have already dates in the course. So try to sign in. You don't need to have officially the credit before it, because like that would be some administrative overhead. But you should have everything like fulfilled to go there. We will not be checking. So if you are somewhere on the edge of it, then maybe, but we'll probably not correct your exam before you have everything done, right? So we don't want to spend the time. It takes like half an hour to correct one exam, and then find out that you are not having the credit, right? So definitely before you want to see a result of your exam, you should have everything satisfied so that you can get the credit. Okay.